Hi everybody. Today I'm going to talk about the eigenvalues and eigenvectors of a linear transformation of a matrix, and we are going to set some examples and solve them in practice. So first of all, what's the definition of eigenvalues and eigenvectors? So which numbers we call eigenvalues and which vectors we call eigenvectors. For this purpose, first of all, I would like to introduce the definition. So let's suppose we have matrix A. It can be matrix A size of 2 by 2, 3 by 3, or in general n by n matrix. And we have the vector x with n coordinates. So if matrix A is 2 by 2, then x obviously vector x is also 2 is a vector with size 2, so two-dimensional vector, is equal lambda times x bar. So let's consider such an equation. The idea here is that by definition, if this equation is satisfied for the vectors which are not zero, non-zero vectors, then the lambda which satisfies this equation this lambda is called eigenvalue. So eigenvalue for this transformation of matrix. And we also have corresponding associated eigenvectors. So the vectors which correspond or are associated to lambda, these vectors we call eigenvectors. So now let's try to give a proper idea what we mean by some examples. Let's take example one. Let's take an easier case. So let's take such a symmetrical matrix A equals, for example, 0, 2, and 2, 0. This is a symmetrical matrix. So you have to be sure that symmetrical matrices have got the real eigenvalues. You have to be aware that the lambdas there can be complex also. So in our courses, we are going to consider the real values of lambda. So that's why we set up such an exercise where we are going to get the real values of lambda. So let's suppose A is equal 0, 2, 2, 0. And our vector x is kind of x1 and x2. These are the coordinates of vector x. And also lambda is the real number which we are going to find. So obviously from the equation ax bar equals to lambda x bar, so a vector x times equals to lambda times x vector x. So let's write everything here. From this equation we get 0, 2, 2, 0 equals to times 2 vector x. Let's write here vector x here. x1, x2 equals lambda times again vector x. x1, x2. So what we do here, we multiply and try to get the system of equations. So we know how to multiply this. We multiply the row by column. So it's going to be 0 times x1. It's 0 plus 2 times x2 is 2x2. And again, the same thing we do with the second row. So 2 times x1 plus 0 times x2 is going to be 2 times x1. It's equal. And do not forget to multiply lambda by this vector. So we are going to get lambda x1 and lambda x2. So again, equality, we next get the equality of two vectors or two matrices. So we know when we can call them equal. If they have the same size and if the corresponding components are equal. So you can see in this case 2x2 equals to lambda x1 and 2x1 equals to lambda x2. Let's continue. So 2x2 equals to lambda x1 and 2x1 equals to lambda x2. So this is a simple system, linear system. How we can solve it? We convert lambda x1 to the left side, so we get 2x2 minus lambda x1 equals to 0. And here we have 2x1 minus lambda x2 equals to 0. So this is, we know, if you remember, we said that this is a homogeneous system. It's a homogeneous system. So let's write homogeneous system. Homogeneous system. We know which systems we call homogeneous. These are the systems which we have on the right side. We have all zeros. So if all elements are zero, all numbers are zero on the right side, so we call this system a homogeneous system. So you know, homogeneous systems always have the zero zero solution. So if we have two variables here, so we are going to have a zero zero solution. A zero zero solution is a trivial solution. So we are interested here with non-trivial solution. So we need to find non-trivial solution of this homogeneous system, because if you remember in our first when we set up the definition, you remember that we were looking for x, vector x is not zero. So the coordinates of x should not be zero here. We are interested in non-zero values. That's why we are interested in non-trivial solution of this homogeneous system. From linear algebra, we know that the homogeneous systems have got non-zero solutions if their coefficient matrix is equal to 0. So let's see, the first comes minus lambda because it's the coefficient of x1. So minus lambda, second comes 2. Here, first comes 2, coefficient x1, and minus lambda equals to 0. So this is the condition when homogeneous system should have non-zero solutions. So from here, from this determinant, we have lambda squared minus 4 equals to 0. And from here, we get lambda 1 equals to 2, and lambda 2 equals to negative 2. So what happens next? Actually, here we have found two eigenvalues. So first eigenvalue is 2, the second one is negative 2. So the rest of the things is to find the corresponding eigenvectors. So in order to find the corresponding eigenvectors, let's take, we will need this system. So I'm going to delete this part here. We are not going to need it. Okay, first let's write our first eigenvalue. Lambda 1 equals to 2. So if you can see, by substituting lambda 1 in the place of lambda in this system, we are going to get what? Look, 2x2 minus 2x1 equals to 0. And 2x1 minus 2x2, again, instead of lambda, we substitute 2. So you can see here we have, from these two equations, we have x1 equals to 2. What does it mean? It means that we have got infinitely many solutions here. For example, if you take x equals to 1, then x1 is equals to 1 again. So actually, if we take x equals to any number c, and c is the real number, then x1 is also c here. So for lambda 1 equals to 2, we have the eigenvectors in the form c and c. You see, so x2 is c, x1 is c. So these are infinitely many vectors for this associated with this eigenvalue. Now let's put lambda 2 equals to minus 2. So hopefully we are going to get the same thing here. So if we take lambda 2 equals to negative 2, we are going to get 2x2 plus 2x1 equals to 0. And 2x1 plus 2x2 equals to 0. So from here, we are going to get x1 equals to negative x2. So the same approach will take us to another infinitely many set of another infinitely many system of vectors. So if we take x, for example, if we take x2 equals to 1, then x1 is equal to -1. So in this case, we are going to get the vectors in the form minus c c. So if x2 is c, then x1 is minus c. So these are the corresponding as or associated eigenvectors for lambda equals to -2. This was an easy example of finding the lambdas eigenvalues and eigenvectors. I hope you enjoyed the video. In the next videos, we are going to promote this idea. You should be aware that the same thing happens with a 3 by 3 matrix or 4 by 4 matrix and so on. The idea is the same. So look what we have done in the beginning. In the beginning, we have here A equals to 0, 2, 2, 0. This is a symmetrical matrix which always will have the eigenvalue, real eigenvalues. So we said that in meantime, we said that there can be complex eigenvalues also. So we started from this vector equation, and then we took matrix A and vectors as x1, x2. So we were looking for lambda first, and how did we find after substituting everything in its place? We got such a system, which is a homogeneous. We said that it gives us the homogeneous system, and we also learned, we talked about some property of homogeneous system for a non-zero solution. We use this fact here. So obviously, we had two eigen values here, which are associated with a set of infinitely many eigenvectors. So do not forget to subscribe to the channel to get the videos here, more videos here. I wish you good luck and success in the exam. See you. Bye. Take care.